So, in the previous lecture I discussed what kind of efforts are being made to create a nuclear fusion reactor in which some isotope of hydrogen will be fused to make heavier nuclei and energy will be produced. This effort is being going on for last 6 decades or so internationally, and still we have not been able to come to a situation where at least the energy which we give to this plasma for heating, at least that much should be recovered through this fusion. The best we have achieved so far, it is say 60% of the input energy that comes as the output. Of course, we are very hopeful coming decades maybe we will be able to create a nuclear fusion reactor, but it has been a very difficult task. But just in front of our eyes, 8 minutes away from us, we have a fantastic nuclear fusion reactor, and that is our sun, where for the last 4.5 billion years hydrogen is being fused into helium and energy is being produced, and that energy is responsible for our survival, all life form on the earth. So, what goes on inside the sun? How that plasma is confined in that volume for such a long time? What kind of reactions are taking place? What are their rates and so on? So, these are the some of the questions that we will be discussing in this lecture. So, physics of the sun or physics of fusion inside the sun. So, let me show you the basic data on sun that I have put on this PowerPoint. So, we'll go to your screens. Now, basic data about the sun, as you can see here, mass is about 2 into 10 to the power 30 kilograms. In comparison, Earth's mass is 6 into 10 to the power 24 kilograms. Then diameter is 1.39 into 10 to the power 6 kilometer, which is 109, approximately 109 times diameter of the Earth. 109 is quite close to 108, supposed to be a very good number in our Indian culture. Then mean distance from Earth is 1.5 into 10 to the power 8 kilometers. So, these are some of the distances mass. Then composition by mass, composition of the sun. As you know, it is all gaseous mass. So, what are the elements in that? And that I am talking of photosphere. I will talk what photosphere is. It is that outer layer of the sun that is visible from Earth during daytime. So, that is known as photosphere, about 500, 400, 500 kilometer thick. So, there the composition is given here, 73.46% hydrogen, helium 24.85, then oxygen and carbon and iron and many more. So, these are the most abundant 5. If I go by atoms, then the number of hydrogen atoms will be more than 90%, and helium is about 9%, and rest is about 1%. Now, sun, the whole mass of the sun, which is very nearly spherical, almost in all directions you have the same radius. So, that you can visualize as composed of 3 different zones. One is core, which is say up to 0.25 of the radius. So, this central here, this is core, and most of your fusion is taking place inside this core up to 0.2 or 0.225 of the radius. So, that is core. And then the next is this radiative zone. This part is surrounding the core, this part is called radiative zone, that goes from 0.25 R to 0.7 R. So, this part is radiative zone. I will just talk why this is called radiative and all that. And next is convective. So, this is convective, this is known as convective zone, 0.7 R to almost the surface. So, that is known as a convective zone, and the surface itself, and surface would mean something like 400-500 kilometers, that is known as photosphere. So, you have convective zones, and after that you have this photosphere, and beyond photosphere also you have some mass which is not visible from here. The densities are too low, though temperature are high, those are coronas and other things. I will be mostly concentrating on what is going on inside this core. Now, the fusion takes place in the core, energy is produced inside this core, fusion energy, and that energy gets transported to the surface, and the temperature in the core is 1.5 into 10 to the power 7 Kelvin approximately, and that is where, of course, that will also vary as you go towards the outer side, outer regions of the core, the temperatures will be low, but mostly the temperature is around that 1.5 into 10 to the power 7 Kelvin. So, here the it takes place, fusion takes place. Now, this energy, as it moves outward towards the sun's surface, there are various phenomena taking place. So, there the role of this radiative zone and convective zone. So, initially in the radiative zone you have these photons are emitted, and where they are very quickly absorbed within few millimeters or so, and then again re-emitted, again they go ahead, again they are absorbed. So, this way it radiates, re-radiates, absorbs, and energy moves in forward direction. So, that is forward means towards the outer layers. So, that is why it is called radiative zone. So, that happens up to 0.7 R. In the convective zone, it is convection. Convection, you are all familiar, in school days you have learnt what is convection. When you put some water or some liquid on a stove, then the lower portion gets heated, and then that lower portion of this material, of this liquid, that rises up, and from that upper portions the colder mass that comes down, you call them convection currents, and that is how the heat is transferred from one place to the other place. So, in this convective zone, which is 0.7 R to almost the surface, that is the heat or the energy is transported in this manner. So, the masses, the hydrogen helium which is there, that masses, they move, they make convection current and take heat from this inner regions to outer regions. And the last 500 kilometers or 400 kilometers photosphere, that is what is visible, it is transparent to the radiation. So, photons straight away come from there to the earth, and that is what we know as sunlight. Okay. So, in the core, the temperature, as I said, is around 1.5 or 1.4 into 10 to the power 7 Kelvin, and the pressure of the gas there, that is very, very high. Temperature is also very, very high, and the pressure is also very, very high. The density of that gas there is, say, 160 times the density of water under normal conditions. So, say 160 grams per centimeter cube. So, that is the kind of density of that gas, and if you calculate the pressure at that density, you can use PV equal to nRT, and the pressure will come out to be almost 200 billion atmospheric pressure. So, at that pressure and temperature, that gas is confined, and naturally it will all be plasma, all the electrons will be away, and from hydrogen, if the electrons are away, you have protons. So, you have a mass composed of protons and electrons, which is that plasma there. Helium is of course also there. And if you look at the outer surface of the sun, which is visible from earth during daytime, the temperature there is around 5780. So, there is a gradient from about 15 million Kelvin to 5000 Kelvin and so on, and pressure of this gas at this in this photosphere, that is also very low. The pressure is about say 0.1 to 0.001 atmosphere, lower pressure as you go out in the outward layer of this photosphere. So, that is the kind of composition. Now, let us come to the fusion, the reaction that is taking place inside the sun. Essentially, all fusion events have to start with a fusion of two protons. You have large number of protons moving with thermal velocities at that temperature, and occasionally two protons will come close enough so that they interact through this strong force and then combine. When they combine, what will happen? Now, of two nucleons, the only stable nucleus is deuteron. You do not have any diproton, you do not have a nucleus of two protons, or you do not have a nucleus of two neutrons. The only nucleus that exists with two nucleons is deuteron, that is one proton and one neutron. So, if these two protons are to combine and make one nucleus, that nucleus has to be a proton and a neutron. That means, one of these two protons has to convert itself into neutron simultaneously. The two protons are fusing to make a bigger nucleus of two nucleons, and simultaneously one of these two protons must convert itself into a neutron. And once proton converts into a neutron, you also have a positron created and a neutrino created. So, you have a proton plus proton, and that will give you a deuteron, and then this positron, and then this neutrino. So, two processes taking together, occurring together. One is governed by strong forces, proton and proton, they have to interact through strong forces to get into one nucleus, and for that typical nucleus time scales are some 10 to the power minus 20 seconds or so. So, that is the time scale in which this reaction will take place. And the other part, proton converting into neutron, that is governed by weak interactions. We have talked about these things a little bit during our beta decay chapter. When proton converts into neutron or neutron converts into proton, that is governed by those weak interactions, and they are really weak. The time scales you can estimate by saying a lifetime of a free neutron. A free neutron decaying into proton and electron and antineutrino, the lifetime is around 14 minutes or so. So, if you convert in seconds, it will be something like 800 seconds. So, that is the kind of time scale for these weak interaction driven beta decays. But here we are demanding that this must occur during that 10 to the power minus 20 seconds, and therefore, the probability of this reaction is very low. The first step, two protons fusing into a deuteron and a production of positron and neutrino, that first step is very slow because of this demand that this weak interaction driven beta decay must occur together with this fusing of these two protons, and it is therefore known as deuteron bottleneck. It is known as deuteron bottleneck, and the probability of this reaction is so small that average lifetime of a proton in that situation, lifetime of proton does not, I am not talking of proton decay or anything, the proton, how much it should be, how much time it should be there before another proton comes and makes it a deuteron. So, that lifetime is around 10 to the power 10 years, or 1 out of 10 to the power 18 protons will fuse, extremely low probability, but still, since the total number of protons present is so large that even at this low probability, some 6 into 10 to the power 11 kilograms of hydrogen or 3.7 into 10 to the power 38 protons fuse every second inside the core of the sun. So, that is the first step of this, and that makes a deuteron. This first step makes a deuteron. What happens after that? As soon as the deuteron is formed and so many protons are there around, so this deuteron and proton, they will interact and they will fuse. So, strong interaction only, no weak interaction coming in. So, quickly it will happen, almost the deuteron is formed and it finds some proton to combine, and then this 3 helium, this will be formed, and of course, some gamma will be emitted. Now, what happens after that? After this 3 He, what this 3 helium will do? This helium will not be able to combine with one more proton, because then it will become 4 lithium. 4 lithium will not exist. With 3 protons and 1 neutron, it will not exist. So, it will not combine with the protons. Combining with deuteron is almost unlikely, because as soon as a deuteron is formed, it is converted into 3 He. So, 3 He finding another deuteron there itself is much less likely. So, what is the fate of this 3 He? One is this: it has to wait for another 3 He to appear on the scene. One 3 helium nucleus is formed, and then it is wandering, thermal motion here, there, and some other 3 He is formed, and then these 2 nuclei of helium with total number 3, 2 protons and 1 neutron, they combine together, and that reaction gives you an alpha particle, a helium nucleus, and plus 2 protons. And 80% of the time this 3 He follows this path. The helium which is created, helium nucleus which is created with 2 protons and 1 neutron, 80% of times it goes through this path and make this helium. What is the other 15%? The other 15% is that this helium combines with the regular helium 4 He alpha particle, which is already there. In sun, this 4 He is already there, say 20% by mass, I said, in the photosphere, and in core it will be even more, because for 4.5 billion years hydrogen is being converted into this 4 He. So, in core you do have these 4 helium nuclei in sufficient number, in significant numbers. So, this 3 He combines with this 4 He, making 7 beryllium. So, that is the that is another route which happens 15% of time. 2 helium, 3 helium 3, they combining, that happens 85% of time. So, if I start with 2 protons fusing, making deuteron, deuteron combining with a proton, making 3 He, 3 He combining with 3 He, another 3 He, making an alpha particle and 2 protons, that makes one full cycle, one full chain, which is known as PP1 chain. So, here it is 2 protons combining to deuteron and deuteron combining to a proton giving 3 He2, and 2 such reactions to take place. So, that I have 2 nuclei, 3 He2 here and 3 He2 here, and that makes this helium and plus 2 protons. And then when you combine all these things together, you get 4 protons making an alpha particle and 2 positrons and 2 neutrinos. So, this is known as PP1 chain, and if this 3 helium nucleus combines with 4 helium nucleus, that another 15%, then what happens? Again you have 2 different possibilities. One possibility is that this 7 beryllium 4, remember this 7 beryllium 4 is coming when 3 He combines with 4 He, from there you get this 7 beryllium, that 15% probability, that combines with electron. Electrons are also there, it is a plasma, so electrons are also there. So, that combines with electron, and then it is one of the protons and this electrons here, that is giving you a neutron and this antineutrino. So, you can have this reaction, a proton and an electron giving you a neutron and a neutrino. Usual beta decay, you remember, proton going to neutron, positron and neutrino. So, from you can bring that positron from right side to left side and you will get this reaction. So, a proton and this electron, they combine to make a neutron. So, 7 beryllium becomes 7 lithium and a neutrino is created, and this 7 lithium then combines with a proton and that gives 8 beryllium, which is also a very very unstable nucleus, which will quickly break into 2 alpha particles. So, this is one possibility, and the probability of that is say 14.9% within that 15%. So, 14.9% probability is that helium will combine with helium 3 will combine with helium 4, making beryllium 7 and then combining with electron, then combining with proton and so on. So, that whole process 14.9%. The other possibility is this 7 beryllium that is formed, that first combines with a proton and that gives me 8 boron. One proton goes here. So, proton number becomes 5 and it is 8 boron, and that 8 boron that combines with electron and that gives me 2 alpha particles and a neutrino. The probability of this event is 0.1%. How do we say this much probability and that much probability? This is all from calculations, computer calculations. We have something which we are receiving from sun, some information, some data we are receiving from sun, the light, how much light is coming, what is the composition of that light, what is the wavelength distribution, all these things are there. And from these we make this solar model, what must have been going on inside, and we know all the nuclear physics of this fusion. So, combining all these things, solar models are created, calculations are made, and from there we know that these are the things. So, that 14.9% thing I have collected at one place, starting with proton and proton making deuteron and that making 3 He combining with 4 He, that combining with this electron, and finally that combining with this proton, and end result is the same. End result 4 proton making a helium nucleus and 2 positrons and 2 neutrino, that end result is the same as what we had considered in PP1 chain. Now, this whole process is known as PP2 chain, and that 0.1% thing where this 7 beryllium is first combining with the proton. So, that also I have collected at one place, and so here it is that 7 beryllium combines with a proton giving 8 boron, and that 8 boron combining with this electron making alpha particle and neutrino. End result is once again same, 4 proton going to a helium, 2 positrons and neutrinos. This is known as PP3 chain. there is one more process by which energy is liberated, fusion takes place, 4 protons combined to hydrogen, and that is known as carbon nitrogen oxygen cycle, CNO cycle. Not much important for Sun, but for heavier stars that CNO is important. In Sun also about 2% of energy is created through that CNO cycle. What is that CNO cycle? If in this gas, if in this core you already have some carbon nucleus, carbon 12. So, if you already have some carbon there, then the CNO cycle can take place. Temperatures needed are slightly higher, and therefore, this process is only 2% or less than 2% in the Sun at that temperature. But see what is the process. One proton going into this carbon, combining, fusing, what does it make? It makes this 13 nitrogen. So, proton going into carbon, already you had 6 protons, one more proton going, making 7 protons. So, that is why it is nitrogen, and total nuclear number capital A was 12, one proton going in. So, that becomes 13. So, it is this 13 nitrogen. Now, this 13 nitrogen, that beta plus decays, right, 13 nitrogen beta plus decays, it gives off this positron and this neutrino, and this proton becomes neutron. So, it again becomes carbon. From 7 protons it becomes 6 protons, because one proton becomes neutron, but that 13 remains 13. One proton becoming neutron, that 13 mass number 13 remains 13, and therefore, you get 13 carbon nucleus. To this 13 carbon nucleus, one more proton goes and combines, and then it will again make nitrogen. 6 protons are there, one proton going on, 7 protons. So, that will make nitrogen, but now the total mass number will be 14. So, you get this 14 N, and this 14 N combines with another proton here, and what will it make? It will make 15 oxygen, and 15 oxygen will beta plus decay, and when it beta plus decays, it will give this positron, it will give this neutrino, and it will give this 15 nitrogen. So, one proton in this oxygen 8, that is being converted into neutron. So, you are getting 7 protons and 8 neutrons, and so you have 15 nitrogen, and on this 15 nitrogen, when yet another proton goes and hits and fuses, then you get an alpha particle and this carbon back. So, we started with carbon 12 nucleus, total mass number 12, and after this whole cycle we created that carbon 12 once again back. So, carbon is not consumed, nitrogen is created and it is consumed, oxygen is created and it is consumed. So, nothing changes in carbon, nitrogen, oxygen composition. So, essentially when I combine all these things, once again the total net result is that 4 protons are being consumed. You can see here the red arrow here, one proton going here, then one proton going here, this arrow, then one proton going here and one proton going here. So, 1, 2, 3 and 4. 4 protons are being consumed, and what are the output? One is here, that is alpha particle, that is helium nucleus, then you have one positron here, one positron here, one neutrino here and one neutrino here. So, it's once again is the same end result, 4 protons are being consumed, one helium nucleus is formed, 2 positrons are formed and 2 neutrinos are formed. So, that is known as carbon nitrogen oxygen cycle. So, that is how the fusion takes place in the sun. Now, a very interesting question is that all right, we have done all these calculations, computer calculations, models, solar models, by which we say that if this is the scenario, if energy is being produced by fusion of protons into helium, yes, this much sun energy I should get at the earth, or this should be the wavelength composition, all these things, fine. But what is the direct evidence of that? This model fits very well with the kind of energy we are getting, and it's good. So, this model is able to explain our observations, but then is there a direct evidence? Can there be a separate mechanism, a different mechanism, which can also give me these results, which can also give me these many joules per centimeter square or per meter square, and which can also give me the same wavelength distribution and all that? How do I know that it is because of the fusion that we are getting this energy? The energy that we are getting in the form of sunlight, that is not coming from the fusion. Remember, fusion takes place inside the core, and from there it goes through that radiative zone and then convective zone, and then it comes to photosphere. And the photosphere, which is transparent to electromagnetic waves, the photons from the photosphere, they cross that layer and come to the earth, and passing from core to this photosphere, this process may take a million years or many tens of thousands of years. So, what we are receiving is only remotely connected to the fusion inside that core. In the radiative region, when the photons are absorbed and then re-emitted and then again absorbed and again re-emitted at different energies, different frequencies and so on. So, what finally comes to photosphere is very different from what was produced inside the core. And also, since if it takes say 1 million years, so not only the nature of that radiation is different, what has started because of those temperatures and those energies, and what we are receiving here are visible and ultraviolet and infrared. So, the nature is different, and apart from that, not only the nature is different, apart from that, what we are getting and its origin, if I find it was 1 million year ago. So, today if I am getting these many joules per centimeter square, that is related to the event in the core which took place 1 million year ago. As of today, how do I know? Even if I understand that okay, it must have been fusion, otherwise I will not get this much of energy. So, how do I know that the fusion is still going on in the earth, in the core? Because if the fusion is if the fusion stops today, we will come to know about it only 1 million year after, because it takes that much of time. So, what we are getting today was created there in the core 1 million year ago. Now, the direct experimental evidence that comes through those neutrinos, those two neutrinos in all these cycles you saw PP1, PP2, CNO and all that, that two neutrinos were created, and those neutrinos, we have talked about neutrinos once again in during our beta decay discussions. These neutrinos very weakly interact with matter, and that is why billions and billions neutrinos keep falling on our bodies and going through our bodies, and we just do not notice anything. The entire diameter of the earth they cross, and the probability is extremely low. out of many billions, one neutrino perhaps will interact with the whole mass of the earth. So, these neutrinos which are created in the core during the fusion, they directly escape from the core, go through all those radiative, convective, photosphere zone and come to the earth almost at the velocity of light. Till last decade we thought that they are really moving at the velocity of light, but now we know that maybe they have very slight mass and the velocity is not exactly c, the velocity of light in vacuum slightly smaller, but still around 8 minutes. So, those neutrinos, they escape from the core and they come to earth, they go in all directions, of course, they come to the earth, and if we can trap those neutrinos, if we can study those neutrinos, and we have done that, we have means it was a very heroic effort of experimentalists. They had trapped those neutrinos, they had observed that neutrinos, and that gives a direct information of what is going on inside the core. So, let us look at the energies of those neutrinos, because when we do experiments on the earth to detect these neutrinos, and we have to make lots of calculations once again how this neutrinos will interact with the detector material. So, energy of the neutrino is also an important parameter, and we see what kind of energy distribution of these neutrinos are there. So, if you think of PP1 chain, this neutrino is produced when these two protons combine to make deuteron. At that stage this neutrino is produced. If you look at PP2 chain, where 7 beryllium combines with electron, and that produces this neutrino here, and in PP3 you have this 8 boron that combines with electron and that produces this nu E. Here the energy is 0.42 MeV, and as it is shared between this positron and this neutrino, the neutrino energy will vary from 0 to 0.42 MeV, a continuous spectrum of energy that it will show up, and the maximum will be 0.42 MeV. That is how the whole concept of neutrino was started. In beta decays, those beta particles were having continuous spectrum of energy, and people were not able to understand how come the Q value can be calculated accurately, and these beta particles are having energy less than Q values, and that too it can vary from 0 to that maximum of Q value. That is how Pauli proposed the existence of this neutrinos. So, both this positron and this neutrino, they will have continuous energy distribution, because the total should be given by this 0.42 MeV, barring some recoil energy that might have small energy that might have taken by this 2H. So, it is a continuous variation. So, that energy is say less than 0.42, but here in these two cases nothing like that. Whatever is the Q value, that Q value is just shared by a very small tiny fraction of recoil maybe here, but almost everything is taken away by this neutrino. So, these neutrinos are monoenergetic and the energy is 0.861 MeV. And similarly here also this nu E, that will take away all the energy that is made available through this reaction, and that is 14.03 or so MeV. So, the ranges are different, 0.42 MeV and less, that is coming from here, and then 0.861 MeV sharp monoenergetic from here PP2, and 14.03 MeV this. Now, how people measured it? The first measurement of neutrino, rather antineutrino, was made long back 1956, but some 26 years after this neutrino thing was conceived, and that was the nuclear reactors. You know, in nuclear reactors the fission fragments are neutron rich, and once the fission fragments are formed, they beta minus decay, neutrons get converted into proton, and in that case a neutron get converted into proton, you have electron and antineutrino. So, this Rhinus group, that Covens Rhinus, they made this first experiment to measure these antineutrinos. The thing was coupled with nuclear reactors where neutrino flux was coming. So, if you want to convert this, it will be P plus nu E bar, P, that will give you N and plus E plus. Right. So, these antineutrinos will react with protons to give this reaction. So, the experiment was to have lots of liquid with free protons and this neutrino flux falling on that, and occasionally a neutrino depending on what is the reaction cross section. Once a while a neutrino will attack one of the protons and this reaction will take place and this positron will be created. Once the positron will be created, it will move in that material, in that liquid, and will find some electron, and then they will annihilate, and 2 gamma photons of energy around 511 kilo electron volts will be generated, and that can be measured by scintillators in the detector volume. So, that is one. Another thing is that this neutron is also produced, and this neutron can be made to get absorbed in some kind of material. So, in that original experiment, it was cadmium chloride mixed in that fluid, in that liquid. So, cadmium is a very good absorber of neutron, you know that. So, this neutron which is created, that gets absorbed into cadmium and takes this higher isotope of cadmium to excited state, and when that de-excites to its ground state, it gives off a gamma ray of energy about 9 mega electron volts, and it should be related. So, appearance of 2 gamma photons of 511 keV, and within microseconds, few microseconds, appearance of 9 MeV gamma, that will give the signal that yes, a neutrino has come and interacted, and that is how the first antineutrinos were measured. In case of solar neutrinos, it will be different because we do not have antineutrinos, we have neutrinos, and if you look at that reaction P going to N E plus nu, from here you can write N plus nu is P plus E minus. So, this is used for solar neutrino detection. Davis experiment, the famous Davis experiment, started in 1964 and first results came in 1968. They used this kind of reaction. Some chlorine, 37 chlorine in the cleaning fluids, double CCl4. Hundreds of tons of that will be needed. So, this fluid in this liquid, the whole thing has to be protected from cosmic rays and radiation coming from there. So, this detector was created some 1500 meters below the ground in some kind of a mine in South Dakota, and there they were looking for these reactions. So, this and neutron will convert into proton. So, that will make 37 argon and plus electron and all that. So, the idea was to search for argon, start with this this cleaning fluid, this C2Cl4 and then wait for some time, and after some time somehow try to separate argon from there and see if the argon is there. That will give the signal that yes, neutrino has been detected. So, it was about say 1 or 2 events in a whole day, because neutrinos interact so weakly with the material that with the kind of solar neutrino flux that we are getting, the kind of detector they made, it was expected that some few neutrinos will come in the whole day. But years of data collection did establish that neutrinos are coming from sun, and they are neutrinos, not antineutrinos. They interact with these neutrons to make protons. So, all these things, but then the number of neutrinos which were detected was only about 1/3 of what the solar model calculation and what the Davis, the experimental setup of Davis, that calculation, all these calculations, all this probability, reaction cross section and all that, what was the expected number and what was the observed number? The observed number was only 1/3 of that. After that, several more experiments were done, that gallium based detector, where gallium will absorb this neutrino and will make germanium, that was there. Then this Kamiokande and super Kamiokande, where the scheme was different. They were looking for just scattering of neutrinos from electron, just a scattering. So, high energy neutrino comes, hits an electron and gets scattered, and electron also gets velocity, and electron can get such a large velocity that would be more than the velocity of light in that medium, and then the Cherenkov radiation will be emitted, which can be detected, and from there this neutrino will be observed. That was the scheme there. So, highly pure water detectors were made, and from those water detectors they tried to measure this. This was sensitive to the lower energy neutrinos also. In the Davis experiment, the cross section etc., it was dominated by the high energy neutrinos. So, PP1 chain, those neutrinos were almost not being counted there, but in this experiment the PP1 neutrinos were also captured. So, here from this experiment the result was that about 60% of expected number of neutrinos were observed. So, consistently all varieties of experiments which were done, of course not many, they were showing that the neutrinos which we observe here is less than about half or about 1/3 of what is expected, if we understand what is going on inside the sun, if we understand how these neutrinos are interacting in our material, if both these theories are correct, if the experiments are done very carefully, the data are analyzed very carefully, then some neutrinos are missing. And this missing neutrino, this problem, solar neutrino problem, remained there for about 30 years or so, 3 decades or so. And then finally, this SNO, Sudbury Neutrino Observatory, they made experiments where all these neutrinos were observed, and there they could distinguish between what we call electron neutrino and 2 other types of neutrino, muon neutrino and tau neutrino. I have not talked much about that, but 3 kinds of leptons are there: electron, muon and tau, and associated with each we have corresponding types of neutrinos and antineutrinos. What we have been talking so far, what is being produced in the sun is only electron neutrino, but there are other neutrinos too, and when these other neutrinos can also hit electrons, can scatter electrons, can break a nucleus. In this SNO experiment, you had heavy water was used. So, deuterons were there. So, these neutrinos can hit the deuteron and break the neutron and proton apart. So, varieties of reactions were possible. So, scattering with electrons was there, then electron neutrino doing this kind of reaction which we have written on the board, that was also possible, and the other neutrino tau and muon neutrino, they can also break the deuteron, giving you proton and neutron. That neutron can get absorbed into some material and a signal from there can also be obtained. So, they could calculate how many electron neutrinos are coming and how many total neutrinos are coming. So, that means, if my detector is only sensitive to electron neutrinos, then I will be detecting this. But if it is sensitive to the other neutrinos and we are finding a total count which is more than this electron neutrino count, tau neutrino and muon neutrinos are also coming, but they are not produced in the sun, because in the sun it is proton going into neutron and so on. These are all, they will all only give electron neutrino. So, from where these tau neutrino and muon neutrino are coming, and when the data are combined, the total neutrinos that are observed in SNO experiment, that total matches very well with the number of electron neutrino which has been calculated to be there from the sun. So, that means, during transit from the sun to the earth, some of these electron neutrinos have changed their flavor. During this transit, some of these electron neutrinos have converted themselves into tau neutrino and muon neutrino, and that is why the detectors that were only detecting electron neutrinos, they were finding less number of neutrons. So, this is known as neutrino oscillations, and this Sudbury experiment was announced, results were announced very conclusively only in 2001. So, it is 1 decade ago in 2001 that this neutrino oscillation has been established, and the problem of missing neutrino which was there for 30 years was resolved. So, that is all about this fusion inside the sun, energy production inside the sun. Our next lecture will be how new elements are produced in a star in general, all kinds of, which we call nucleosynthesis.